Hello everyone, welcome. And today we're going to be looking at alkanes in AS chemistry. So, alkanes, how can they be formed? Firstly, they're mostly formed through addition reactions, and this is when hydrogen gas and an alkane are heated and passed over finely divided platinum or nickel catalyst. So when alkenes are passed over platinum and nickel catalyst with hydrogen gas, it produces an alkane. So let us take the example of the reaction 1-butene, which turns into butane. Here, so this is a displayed formula of 1-butene. The butene is on the double bonds on the first carbon, and there's the correct amount of hydrogen 1, 2, 3, 4, 5, 6, 7, 8. So this is C4H8. Now, what happens is then this is passed over heat with platinum slash nickel catalyst. We will be understanding the mechanism, what's behind it, which happens. But for now, just learn this. The double bond breaks and the hydrogens are added. So we can just draw the same structure again, but again the hydrogens will be there. And I will not draw the hydrogens, but you guys can see the hydrogens will be there, and it will form an alkane, which has the formula of CnH2n plus 2. Now, let us understand what cracking is. It's another form of making a alkane. So, in cracking, large, less useful hydrocarbon molecules, which are found in crude oil, are broken down into smaller, more useful molecules. So, basically, the process, we'll look into this later on, is when the large hydrocarbon molecules are fed into a steel chamber, the fractioning column, and they're heated to a very high temperature, and they pass through an alumina oxide catalyst. And this causes the large hydrocarbon alkene to be broken down into smaller alkanes and alkenes. So now this is the main point of the entire chapter, free radical substitution. And alkanes can undergo free radical substitution in which a hydrogen atom is important, gets substituted by a halogen. Over here, this can also be a hydroxide. And this requires UV light, so sunlight, which is needed for this substitution to occur, which we'll look into later on. And this is a type of substitution reaction. So now let us look at the first step. The first step is called the initiation step. So what we're adding basically a halogen to an alkane. So what is a halogen? Let's take the example of Cl2. And what happens here is the UV light. So if we draw the diagram, this is chlorine. The UV light causes the bond to break homolytically. So what does this mean? That means each chlorine will get one electron. And this is a very important thing you need to know. You need to draw half arrows to represent the chlorine being broken and forming a free radical. A free radical is basically when there's one or more unpaired electrons in an atom or ion present. So we would draw over here chlorine with an arrow. This is a half arrow with a dot. This shows us a free radical, and plus another chlorine with another arrow with another dot, which shows another free radical. So two chlorines are being formed here, and this is the initiation step. Now we will look at the propagation step. This is where most people get confused. Let us take the example of ethane. So I have CC, I have the carbons here. I'll just draw the hydrogen on the first one. So since UV light is being present, homolytic fission will still happen in this atom. So imagine I have CH. Homolytic fission into UV light will still happen over here. So another free radical will form. So C, and then over here CH. This will form a free radical plus this hydrogen is the free radical. Now, what about the initiation step? There are chlorine free radicals present in the system also, right? It is a fact that free radicals are very attacking. They like to react with each other. So what will happen is this chlorine free radical will react with the hydrogen free radical. So what would be the form? So we would have a CH3 CH2 radical, and then plus what this will react with is this hydrogen to form HCl. And this is one of the products that's formed in an addition reaction. This is the byproduct. Now, you may ask, there is this free radical also. Why doesn't this react? And actually, this will also react. This is part of the termination step, but another part of the propagation step is this reacting with chlorine 2. And this will produce CH3, CH2, Cl plus a chlorine radical again. So this free radical reacts with chlorine to produce the product which you want is chloroethene. Now, what is left in the system? The things that are left in the system is this free radical and this free radical, which takes us on to the termination step. Let us draw the two free radicals. We have CH3, CH2 free radical, and then chlorine free radical. So these can react in any way together. So one of the compounds that can form the termination step is chlorine plus chlorine again. So this can form chlorine 2. It will not prioritize anything. It will react with any free radicals have, so it will form this. Another thing that can form is CH3, CH2, and this can react with another CH3, CH2 free radical, and this will form a CH3, CH2, CH2, CH3. This will form butane, right? And finally, the process we really want to know, the real reason, is CH3, CH2 plus a chlorine free radical with this free radical will form CH3, CH2, Cl, which is the end point of our free radical substitution progress and mechanism. Its mechanism. So this is the end of our free radical mechanism. Now let's look at cracking. When a large hydrocarbon is cracked, a smaller alkane is formed, which you know. So an example of this could be the cracking of decane, which is a large hydrocarbon, which is turned into smaller octane, which is better combustible, and ethene, which is a alkene. And the low molecular mass alkanes make good fuels and they're high in demand because they're more flammable, they're more volatile, so there's less energy that is required. And then it also produces alkenes, which are used for other reactions. Since ethene can be used in polymerization, ethene can also be used in the hydration of ethene to make ethanol, and this is in many other reactions, and this is called feedstock. So this is why the alkene is also useful. Now we'll be learning why alkanes are very unreactive. What are alkanes? C and H, right? Firstly, there's a lack of polarity. If you look at the dipolar scale, which is used to measure electronegativity, these have a very similar electronegativity, so there will be a very little chance of a dipole or a permanent dipole forming. So it is not polar, hence it will not react with any polar agents. An alkane consists of carbon and hydrogen atoms which are bonded together by single bonds. We're told that covalent bonds have a very low melting point. However, this is not true. This is a very weak intramolecular force, but they have a very strong intermolecular force. So a lot of energy is required to break this carbon-hydrogen bond. That is why it is very unreactive. Carbon monoxide is formed when there is incomplete combustion of alkanes, and this is bad because carbon monoxide binds to the hemoglobin in our blood cells irreversibly, so it cannot be unbound, so our body can carry less oxygen, which is obviously bad for us. And now, normally nitrogen is very unreactive with oxygen in the air, but since the combustion is taking place in the car's engine, it has a very high temperature and pressure, and this causes the nitrogen to become oxidized. So this forms nitrous oxides, and these nitrous oxides can dissolve in water to form acid rain, which can corrode limestone and damage aquatic life. But also, the car's exhaust flames have unburnt hydrocarbons and fuels and there are different oxides which are called VOCs. And these nitrous oxides can react with these VOCs to form peroxyethyl nitrates, which is called PAN. And this is a very important pollutant. This is the main pollutant in photochemical smog, which can affect and damage our lungs. And let's just do some practice questions now. So, crude oil contains a mixture of hydrocarbons, they're separated using fractional distillation, which you know. Further processes can be carried out, including cracking. So what is meant by the term cracking? Cracking is a term which a process. cracking is a process of breaking down a large hydrocarbon into smaller hydrocarbons, which consist of alkanes and alkenes. And cracking is carried out to form low low carbon low carbon chains, alkanes, which are much more volatile and reactive and hence better fuels. And is also used to form alkenes, which are used in feedstock for multiple other reactions. Stated two conditions react for cracking of alkanes. Well, we need to have a high temperature. We need to have a very high temperature, as well as having the catalyst silica with aluminum 2 oxide, dialuminum trioxide. And construct a balance equation for the formation of heptane from the cracking of the product tetradecane. So let us look at this. So we know C7H16 is formed. This is an alkene, and this is also an alkene. So C14H30, and then it forms C7,6,16. So we have 7 carbons left, and we also have 14. We have also have 14 hydrogens left, right? So it's 14 minus 7 is 7 carbons and 14 hydrogens. So what can we form over here? There's multiple answers for this question, but we can form, which is the easiest to me, is 2 alkenes. So we can form C3. So we need to find 2 other products. It can be C3H6 and then C4H8, which adds to 7 carbons and 14 hydrogens. And then many other answers, as long as it adds up to 14 hydrogens and 7 carbons, it will be correct. Now, another alkene, C8H18, is used in gasoline. This is called as octane or petrol. It undergoes combustion to produce a mixture of products including carbon monoxide, oxides of nitrogen, and unburned hydrocarbons. Explained by carbon monoxide dangerous inhaled, like we talked about, it will bind to our hemoglobin irreversibly, so our body can carry out less oxygen, so less respiration will occur. And describe the environmental effects of oxides of nitrogen and unburned hydrocarbons. So oxides of nitrogen can dissolve in water in rain to form acid rain, which can damage aquatic life and corrode buildings. And oxide of nitrogen can react with hydrocarbons to form PANs, which cause photochemical smog. Now, let's look at the next question. Alkanes are generally unreactive and do not react with acid, bases, or with oxidizing or reducing agents. However, they will go with react with halogens under suitable conditions to form halogen alkanes. Methane reacts with chlorine in the way to form chloromethane. This is the type of reaction that occurs in this reaction. So like we talked about, this is a free radical substitute reaction. Now, 2 test tubes are set up, each containing a small amount of methane and pale green chlorine gas. One test is left in the dark, whereas the other is placed in direct sunlight. Explain the observation that you would be observed in each test tube and give an equation for the reaction that occurred if applicable. So, what we know is we need UV light, which comes from sunlight. So if I have a test tube which consists of chlorine, we have chlorine gas over here, and contains methane, there will be no reaction since we need the UV light for homolytic fission to occur. So what would be the observation here? No observation, or the color would stay pale green, pale yellow. And this is because we need UV light for a reaction to take place. And now the container which contains the chlorine as well as receiving sunlight, so UV light, it will undergo free radical substitution. So the reaction would be CH4 plus Cl2 to form chloromethane, so CH3Cl as well as HCl, right? And this will form, and the color change, it will turn colorless as chloromethane doesn't have any color. Now let's go to the next question. Explain the type of bond breaking that occurs in the initiation step. So like we learned about homolytic fission will occur in the initiation step, and this means that each atom in the covalent ball will get 1 electron each. And a free radical is an atom or ion that contains at least 1 or more unpaired electrons. Explain why the CH1 in the alkene does not break in the initiation step of the chlorine bond. So this is something easy to learn. The carbon hydrogen, since we learned the carbon hydrogen is very unreactive, this will require a large amount of energy. So as we looked at, carbon and hydrogen is very unreactive. The bond strength is very large. That is why they do not break easily, and the chlorine can break easily, and the carbon hydrogen requires more energy. Now, the final question we have is name each step of the reaction between methane and chlorine as described in part A, include relevant equations. So firstly, we learned about initiation, then we learned about propagation, and then finally we learned about termination. So initiation, we need to draw the arrows. So Cl2, like I showed you guys, you need to draw the half arrows into a radical with the arrow. It's not really good. And here, and then over here. So we can see this is the initiation step. And propagation is the reaction. So it can be CH4. So in CH4, there can be in CH4 there's two things that can happen. The CH bond can break, so this will form a CH3 free radical, and then there's a chlorine there'll not be a chlorine, there'll be HCl, right? HCl will form, and then we also have another one, CH3. The radical can react with chlorine, form CH3Cl plus chlorine radical, right? This is a propagation step. And finally, in termination, I forgot to show you guys, you should draw the half arrows again. So we can have CH3, and this will turn with chlorine over here, right, to form CH3Cl. And again, we can have this with CH3, or we can have with chlorine and chlorine. So thank you guys, and that is everything for today. And thank you for watching, and best of luck for your exams.